Hi everyone, my name is Pablo Gardela from the Buenos Aires Institute of Technology and Allegro Microsystems, Argentina. In this presentation, I will show the results of our paper entitled Analysis of the Impact of the Monitoring Equipment on the Common Mode to Differential Mode Conversion in Bulk Current Injection Tests. In this presentation, I will be first introducing BCI, which stands for Bulk Current Injection. Then I will present our case studies and give a theoretical framework for the developments. After that, I will be covering the experimental results, both with measurements and simulations. And finally, I will present the discussion and conclusions of our work. A typical BCI setup is shown on the right. It is composed of an artificial network, an electric load, a wire harness, some injection and monitoring probes, and of course a DUT. It's typically composed of an IC, some external devices, and a PCB. The goal of this test is to provide a good correlation with the real application. That's why these tests are called system-level tests, because they try to mimic, for example, harness resonances or the application circuits that will be used in the real life events. However, on the other hand, we have the IC level test, for example, direct power injection, which can be thought as a Thevenin equivalent of this BCI test, which provide like what is called laboratory conditions, because they don't have harnesses, they have specific PCBs with different boundary conditions, and therefore their reproducibility is much higher because all the conditions are much well controlled. However, that comes at the lack of correlation with the real life. So on the one hand, we have IC manufacturers which prefer this IC level test, and on the other hand, we have auto parties or automobile industries which prefer the system level test because they have the correlation with their environment. So it comes as a conclusion that having accurate models of this test setup is crucial for converting a BCI or a vehicle level specification into an IC level specifications. Therefore, that allows IC designers to include EMC simulations at early design stage in the design flow process. As the name of our paper suggests, our work is concerned about the impact of the monitoring equipment on this system level test. We have realized that very little work has been done studying how the monitoring equipment can impact the BCI setup, and also very few guidelines are provided in the ISO standard. So on top of that, on the other hand, we have technology developments and functional safety requirements which are driving developments like the electric vehicle or the hybrid electric vehicle or the ADAS, among many others, in which some functional safety requirements typically come in the form of redundancy or system in packages structure, where we can have even multiple dies inside a single package. And in regard with BCI, there's not a clear guideline of how should these devices be tested. For example, should we test them simultaneously or not? Of course, that is something that needs to be agreed between parties, but there are very few guidelines regarding that, and also how much the monitoring equipment will impact during this testing is not quantified in the state of the art. So that's basically what this work tries to address. First of all, a quantification of the problem of including the monitoring equipment on the BCI setup, and also some analysis and evaluation of mitigation strategies. This, of course, is for guaranteeing the accuracy of BCI simulations and to provide a higher degree of reproducibility in the lab. For studying the BCI setup, we will follow a divide and conquer approach, which is the typical strategy followed by the state-of-the-art. In this approach, we assume there is a single-ended Q10 propagation mode on each of the cables, and we split the setup in some common elementary blocks, like the harness, the DUT, the electric load, and the artificial networks. So one of our case studies will be a 2-wire open loop or substitution harness, because we will not have the monitoring probe. And on the other hand, the second case study will be a 3-wire closed loop setup, in which we do have the monitoring probe. In both cases, we will have PCBs, in which there is a transmission line with a ground plane on the bottom layer. So the network that we will characterize is this one. We have our transmitter, the red box here, an anti-aliasing filter, and some input cables. Since this is a 2-port network, we can express the impedance parameters in terms of the single-ended voltages and currents. However, it is more meaningful to express this matrix in terms of the modal impedances. So if we do the math as we've done in the paper, we can come up with this model in where the modal impedance matrix is expressed in terms of the differential mode impedance, the common mode impedance, and the mode conversions, which, thanks of the reciprocity of this network, the common to differential mode conversion is equal to the differential to common mode conversion. That means that this impedance is the same regardless of the branch. So our characterization setup is this one. We have placed our transmitter equipment in the ground table, and we have defined 3 different planes. The first one is the one right at the transmitter input, then another plane at the AA filter input, and another one at the point in which we would connect to the BCI setup. Also, we have defined 3 different situations. In the first situation, we have the transmitter right on the ground plane, and in situation 2, we have included a galvanized steel support for keeping the same interaction between the transmitter and the plane, but changing the interaction between the cables and the AA filter, with the plane, of course. And in situation 3, we have changed the supporting material in order to change this common mode impedance, but keeping the same interaction between the cables and the filter to the table compared with situation 2. So by doing that 3 different situations and analyzing the results in the different calibration planes, we have been able to take some conclusions. For example, in terms of the differential mode impedance, when we measure the impedance at the transmitter input with a network analyzer and then convert that to impedances, we've seen a differential capacitance, basically. This is the red and blue line here. Then as soon as we measure the differential mode impedance at the filter input, we've seen these low frequency peaks. These peaks are given by the rejection band zeros. I mean, the impedance that the filter presents to the setup, I mean the input impedance of the filter, is an important parameter because it's loading the setup. And this is something that has not been considered before, at least not that we are aware of. Then as soon as we move to the last point, the one in which we will connect to our BCI setup, we found an additional resonance at high frequency given by the cable's inductance and the load capacitance. Then in terms of the common mode impedance, as we were expecting, the situation 3 is the one that shows the higher common mode impedance. You can see situation 1 and 2 practically shows the same. And also the high frequency resonance is a little bit higher because of the capacitance, the common mode capacitance being lower. Besides that, the mode conversion, I mean the relation between the common mode current and the differential mode voltage, for example, is lower in situation 3 also. So by looking at these results, it shows that situation 3 should be like the best scenario for having the lowest impacts on BCI. So our next step is to perform the system level BCI simulations. For doing that, we have two different setups in Cadence, composed by the several blocks that we've been characterizing with BNI measurements, and the PCBs, which are the only ones that are based on electromagnetic simulations. Then in the two-wire situation, for example, what we simulate is the insertion loss between the input port and an output port in the IC position. The results are shown here, and we can see that in the three different situations, and in the ideal case where we only have the differential impedance specified on the user manual and no common mode impedance, the performance are quite different. In fact, we can see that it's not sufficient to be in situation 3 in order to provide better accuracy and correlation when compared to the ideal situation. Then for the three-wire situation, when we analyze the insertion loss to the BCC port, we can see something similar up to some frequency where the bandwidth of the capacitors is good enough for filtering the impedance variation, basically this capacitor. Then the insertion losses are essentially the same. But beyond that frequency, we can see that the differences can be as high as 20 dB or so when compared with the ideal situation. And in this case, it is interesting to realize that situation 3 has at some frequencies more deviation than the other ones when compared with the ideal case. So being on situation 3 doesn't seem to be like a guarantee of anything. And finally, when we analyze the insertion loss to the output resistor, we can see something similar. Up to the self-resonance of the caps, the thing is pretty good. Beyond that, we see some differences, and there's no guarantee, as we were saying before. The larger common mode impedance and the lower mode conversion that we propose with our approach are not enough for guaranteeing better accuracy of the BCI simulations. So we found differences in the common to differential mode conversion between 2 dB and 23 dB. Therefore, we conclude that disregarding the monitoring equipment can not only compromise simulation accuracy during the early design stage simulations, but also lab reproducibility, which can be a serious concern when testing in different facilities. However, it is true that our results are completely dependent on the topology that we use and on the values that we assign to the devices. However, we expect that the concept behind our work can be completely extrapolated to other situations. We don't expect variation in terms of the monitoring equipment loading the setup, even for different harnesses lengths or probe positions, or even with more wires. So the loading will still happen, and if the circuit is not able to compensate those impedance variations, then it is expected to see a variation in the insertion loss to the load. So in order to mitigate this, we propose the use of the test bench transfer impedance. This quantity is defined in the ISO standard as the common mode voltage injected in the injection probe position divided by the current seen by the monitoring probe current at its own position. That quantity has units of ohm, and therefore it's called test bench transfer impedance, and it's a fingerprint of the real setup, basically, which, among other things, it inherently incorporates the loading of the monitoring equipment. So our proposal is to use this quantity as a fingerprint of the actual setup. And in regard with the system in package evaluations, we consider this work is a proof of concept that if loading one output at a time, we may run into a lack of accuracy during simulations and testing, as we said before. So we consider that in case of dual devices, like the one I showed before, all the outputs need to be monitored simultaneously, or at least in the same conditions as they will be used during the real application. That's why that's the only way we consider we can keep the correlation with the real application, which is the ultimate goal of this kind of system level tests. And in order to sum up, we have showed that the monitoring equipment can impact the common mode to differential mode conversion in bulk current injection test, and we've analyzed and evaluated different mitigation strategies. We've shown that even commercially available equipment specifically designed for EMC test can load and change results, in particular when they have non-ref and unbalanced interfaces. So our recommendation is to use the test transfer impedance as a signature of the actual test setup. And on the side of the standard regarding the system in package testing, we recommend addition of guidelines for future revisions of the ISO standard. Last but not least, in terms of future work, we are planning on doing a study of the reproducibility of the BCI transfer impedance by performing an interlaboratory comparison. So volunteers, please reach us out if you want to join this experiment. Thank you very much for your attention. I will be looking forward to hearing from your questions and feedback, and I hope to see you soon at the symposium. See you, and thanks for watching.